Okay. Some notes for example 5-1. So we have here, determine the adequacy of a 4x14 hemisphere with grade number 1 and better sawn lumber beam to support a concentrated moving load of 2,000 pounds. The beam span is 15 feet, normal temperature and right service conditions apply, and the beam is laterally braced at the supports only. The available bearing length is 3 inches, assume a wood density of 36 pounds per cubic foot, and then load duration factor equals 1, creep factor equals 1. Then our given are, for the dimensions, so we will use the standard dressed size, the exact dimensions being 3.5 by 13.25. It's already given in the problem that the wood density is 36. And then for the beam span, well, the span is given, also the bearing length LB. But why did I choose 15 feet? Because it is assumed that the problem is already pertaining to the beam span L, okay? Since that's also our terminology. So beam span L equals 15 feet, and that means it is from the center of the bearing length to the other center of the bearing length, okay? And so beam span L equals 15 feet, and then bearing length equals 3 inches. Now for the unbraced length, it depends on the lateral supports, right? Stated in the problem that the lateral supports are in the ends only, okay? It's lateral brace at supports only. That's only the ends, and therefore LU equals L equals 15 feet. We have a moving load 2,000 pounds, and then reference design values already provided. CD equals 1, K equals 1. So let's start. We'll solve first the bending stress and strength. For the stress, we need to get the dead load and the live load. For dead load, it's just the self-weight. So the density times the dimension of the beam being, the weight being 11.594 pound per feet. And then we get the moment for uniformly distributed load, which is 1/8 WL squared. That's the maximum value already at the mid-span. And then how about the live load? As you can remember, this is a moving load. And so we place it at the critical point of the beam, which would be what? At the mid-span. Right? We place the concentrated load at the mid-span, and then we have a shortcut formula here, 1/4 PM. You can check this if these are the formula, indeed the formula for such cases. And so we have a moment equal to 7,826 pound-feet. And then the stress is using the derived formula from exam 1. Okay, so you should have already memorized this by now, 6m/BD squared, and then our bending stress would be 970 PSI. Now for the strength, we need to compute for RB, but before computing RB, we need to compute for the adjusted E-min. And that would be equal to CM CT CI times E-min. All of these are just 1, and so E prime min equals E min equals 550,000. I've also computed E prime here, but that would be used later on. And then next, as you can remember, we need to use the table for computing the effective unbraced length. Also, you need to compute for LU over D. And so we have after computing for this, we have the unbraced length, effective unbraced length, equal to 27.763 feet. Then, mechanical na lang yung mga next steps. RB equals 18.98. And then FB would use E prime min also, and RB. So we have FB, the Euler stress, equal to 1,831. And then next, we compute for the adjusted FB prime. And before that, we need to compute for FB star, as you can remember. Right? FB star, where's that? There, FB star. Okay? FB star is just all of the applicable adjustment factors except CFU and CL times FB. And I cannot write in the software FB star, so I wrote FB prime prime. That would be our FB star, okay? So all of the adjustment factors except CFU and CL multiplied by FB, of course. So that is 1,100 PSI. And then computing for CL, we have 0.939. And since FB star is already all of the adjustment factors except CFU and CL, we can compute for FB prime by multiplying FB star by, well, CFU and CL, which would be 1033 PSI. Now we compare that with the stress. This is the adjusted design value. We compare with the stress being 917 PSI. And so, what is our conclusion? It is adequate, right? Next, we compute for shear. We already know how to compute for the strength from the previous chapter. And how about the stress? The first question is, where would you put the concentrated moving load? Since this is a moving load, it can occur anywhere in the beam. And since it's just a single load, you put that where? At the support, right? And then, computing for the shear force, we have half of the uniformly distributed load plus the concentrated load, which would be 2,090 pounds. Computing for the stress, again, derived formula, we have 68 PSI. And then we compare that with FV prime, the adjusted value. Okay, just a note with regards to the previously discussed critical shear value. We have said that we can use the D distance, right? But I did not compute for the D distance value of shear. Why? Because there's a caveat, which is provided that no concentrated load occurs in this region. But we put the concentrated load at the support. And that would violate this caveat, and therefore, we need not compute the distance. Okay? And so, we compare the stress with the strength, still adequate at that point. Okay? Next, deflection. So, I already computed for the moment of inertia, and as we have mentioned in the lectures, it is divided by two criteria, live load deflection and then the total load deflection. For live load deflection, we have L over 360. And then there, L over 360, which is 0.5 inch. Now, to compute for the actual deflection, it depends on the loading configuration. Okay? And since this is live load, that would pertain to the concentrated moving load, where should we put the live load for maximum deflection? There's only two answers, of course, no, in all these questions. It may be in the midspan or in the support, because there's where the maximum values occurs. And in the case of deflection, as you can imagine, it should be in the midspan, right? So we use this formula here. So PL cube over 48 E prime. Okay, remember E prime. I. And then 0.239 compare with 0.5 inch and therefore still adequate. Next, we compute for the total load, which is a function of the dead load and live load. Already got the live load, we compute for the dead load. And it is a uniformly distributed load since it is a self-weight. And so we use this one. This is another formula here. And then we got 0.013 inch. And then we get the total load, but we need to find first K. What is K? K is 1 for green or unseasoned lumber or blue lamp used in wet service conditions, 1 for seasoned lumber used in wet service conditions, and 0.5 for seasoned or dry lumber, blue lamp and prefabricated I-joists used in dry service conditions. But in our case, K was already given, right? 3 factor K equals 1. And so, we can compute for the total load, total deflection, 0.252, comparing with L over 240, still adequate. Okay? Just a note. We have computed 3 limit states already, but let's say that in one of these limit states you have already have an inadequate section. Do you need to proceed to the other limit states for us to know if it is adequate? No need, right? Because only one of these limit states fail. It has already failed. Okay. But in our case, it's still adequate, so we compute for the last limit state, bearing. Again, the question here is, where do you put the concentrated load? Middle or in the support? Bearing is related to reaction, and so we put the moving load at the support. Okay. And then we have R equals 1086 pounds. Computing for the stress, we divide that reaction with the bearing area. The bearing area is equal to the thickness times the bearing length. It's already provided, and so we have around 200 psi. Comparing that with the adjusted design value, 1350, still adequate. We did not compute for CV, or rather we have a CV equals 1 because this is not an interior support, it's just at the ends. And so CV equals 1, and since for all the limit states it is adequate, therefore the member is adequate. Okay?